In this video, I'm going to be talking about projectile motion, which is motion that has both a horizontal and a vertical component. The important thing to remember with projectiles is that the only force acting on this object is gravity. Projectiles include objects that are dropped from rest, like our illustration of a ball just being dropped off a cliff, or objects that are being thrown vertically, either it is an absolute, as much as possible, straight up vertical or launched at a slight angle, as we see in these other two illustrations. Projectiles, once they have been launched or projected or dropped, will continue in motion because of inertia. An object in motion stays in motion. No matter what direction of the motion is, whether it has been dropped and so it seems to be moving straight down, or it's been thrown upward at some angle where it seems to be moving upward and then downward, the only force, remember, acting on this projectile is gravity. So let's just talk a little bit about this movement. These projectiles move in two dimensions, and so it can be moving upward and to the right. But it's not going to have an upward or rightward force acting on it after the applied force has launched it, so after it has gotten into motion. Gravity will be acting on that object, and it provides a downward force and a downward acceleration. But remember, acceleration doesn't tell you about the motion, the direction of motion of the object. It tells you how the velocity is changing. Is it becoming faster? Is the object speeding up in its motion, or is it becoming slower and slowing down? So a projectile can be moving upward and still be slowing down. So just to say it again, because this is really where it seems counterintuitive based on what we think is happening with objects. In a projectile, gravity is only affecting the vertical motion. It's only determining whether an object's acceleration in an upward and downward direction is changing. It is not affecting the horizontal. There is nothing affecting the horizontal motion. It is just carrying on because of inertia. So let's think this through. If we didn't have gravity and an object is launched, in this case we're using a cannon, launching a cannonball off a cliff. If an object is launched in a horizontal path, it's going to continue in that horizontal path if gravity is not present. So this gravity-free zone, and that's what we see happening in space in a no gravity situation. The object continues in motion in its initial path. That's inertia. That's Newton's first law. But of course, that's not what happens in our space that we live in on Earth, where gravity is very present. So when gravity is present, it is going to be exerting a force in a downward direction to pull this object downward over the course of its time. And if you look at a time-lapse photograph of a projectile, you will see this is actually true, that objects will move horizontally the same distance. So at each, say these pictures were taken every second, each second, this distance is going to be the same whether the object is moving on a flat horizontal path or on this descending parabolic trajectory. The horizontal change is going to remain constant, but the vertical change is where we're seeing the force of gravity pulling this projectile closer and closer to the Earth. So we call this two-dimensional motion. Projectiles are moving upward and downward. That's one dimension. And then horizontally. And somehow I lost my second word. So this word here, we should have dimensions here. I don't know what happened to it. These two components are independent of each other. So one does not affect the other. So we have to think about them separately, even though they work together to create this final path. Again, gravity only affects that upward-downward path, so it only accelerates in a downward direction and does not affect the horizontal path. And again, I should really have put this, the change for a acceleration downward is going to be our standard force of gravity, which is acceleration of gravity, which is 9.8 meters per second squared. Now, we don't usually launch things at a flat horizontal path, so things are usually launched in an upward direction to some extent. But the same thing applies. So we have a little illustration here showing if this cannon is launching in a slightward upward direction, if there was no gravity and a gravity-free path, then this would be the change along a straight line, just pointed in whatever direction the cannon is pointed. But of course, we're going to have gravity pulling it down, so it makes a nice parabolic trajectory. It doesn't have it has an upward curve and a downward curve, and the amount of upward curve is going to be influenced by the force, that applied force, that sets that projectile in motion to begin with. It doesn't matter the angle of launch, though, because gravity is going to pull that object with the same amount of downward acceleration each second as if it was being dropped at rest and if it was just going straight down. So remember, there is, again, no horizontal acceleration. The only thing happening here is vertical. Horizontal movement is due to inertia. So we can use our vector arrows, which, remember, they point in the direction of the acceleration, and they give some sense of the magnitude by the size of the arrow. So we can use these vectors to create vector diagrams that show both the vertical and horizontal velocities of a projectile. So our initial vector in the x direction, so thinking about our xy direction in a graph. So in our x direction, we have this is being launched at 20 meters per second. And so every second, it's continuing to maintain that same velocity of 20 meters per second. And you could figure out, how far it has gone by thinking about, okay, here's 20 meters, and here's 20 meters another second, and here's another 20 meters. So after 3 seconds, we've moved 60 meters. Very simple additive math. Now along the y-axis, and in this case it'll be negative y because the direction is downward, the force of gravity is pulling on this object with the 9.8 meters per second per second. So every second we have an acceleration that is 9.8 meters per second, or the velocity that is 9.8 meters per second faster. So the total acceleration is 9.8 meters per second, or per second squared. And of course, most of the time in math, we're just going to round that up to 10. But in this diagram, we are showing it with 9.8. So our initial y acceleration at this point of launch here is going to be 0. But after that first second, acceleration will have kicked in and is going to be a negative or downward direction, 9.8 meters per second. So that's our velocity after 1 second. And then after this second, we've had 2 seconds go by, so it would be 2 times negative 9.8 or a negative 19.6. And then after 3 seconds, our velocity in the y direction has tripled from initially, so we have a negative 29.4 meters per second, and so forth. And so again, we're considering the force of gravity. It's only acting on the y direction, and each second is accelerating the velocity by 9.8 meters per second. So when objects are launched, especially if they're launched in close to vertical position, we have an object that's going to go upward and then turn and go downward. But gravity is still creating downward acceleration on these objects moving upward. What happens is that they'll gradually slow down from their initial launch velocity, pause briefly at the very, very top, at the vertex, and then experience increasing velocity as they move downward. Again, horizontal velocity is still constant, and in a perfect world where there's not air resistance, you could actually see that their change, like you could draw a line. Here's after the first second being launched, it's going to be, equal with this path coming down, and it's a beautiful, perfect, symmetrical parabola. In real life, it tends to fall a little bit, more this way because air resistance will change that path. But we're considering kind of a perfect world. And so again, each time in this path, we've got a certain constant horizontal distance change. So in this case, it's 12 meters per second. Horizontally, again, after the next second, it has moved over another 12 meters. So this distance in here is 12 meters. And again, each second, it's moving that much horizontally. But our acceleration, starting off at 19.6 meters per second, the initial force to get that object in motion, sets it in motion at that particular velocity. Then after 1 second, we will have subtracted 9.8 meters per second from this 19.6, giving us a velocity of 9.8. The numbers have been picked, obviously, to make it nice and easy. At that peak, there is no downward acceleration, downward velocity. There's still acceleration acting on it, but there's no velocity because it's going to pause briefly. And then as the projectile kind of goes over the curve and falls back to Earth, we see negative velocity increasing again, 9.8 meters per second each second. So check for understanding. Do you understand? Can you explain? What do we mean by this word projectile? Something that is dropped or is launched in some horizontal or somewhere between a horizontal and a vertical direction. Can you explain how a projectile moves both vertically and horizontally, that it's moving in 2 dimensions? Can you identify which component is affected by gravity and why? Can you sketch the path of a projectile launched from a horizontal position or one that's launched a little more vertically from a non-horizontal position? And if you've been given those initial horizontal and vertical velocities, can you predict the location of the projectile at a specific second from launch using what you know about how that velocity is going to change over time? If you're not sure about any of this, go back and rewatch the video. Otherwise, I will see you in class.